Hello my great friends, IBM is here with another episode of Learning Physics, and today I will not waste any much time. I would like to take you to part 5 of waves and superposition. Do not forget to check in the video description to get the links to the documents. Just go to the video description, there are links to multiple choice past paper questions. There's a link to paper 2, there's a link to paper 4. Because we have already solved paper 4 and paper 5. So don't forget to go to the video description which has been attached on this video so that you check them out. There are those students who always write me an email to get documents for multiple choice. Please check in the video description. The first link, I think it is for the multiple choice questions. They are organized per topic. So without wasting time, let's go to our past paper document. So this is, I think we stopped around here in episode 4. We stopped on page 96, I think, and we were supposed to start with this particular question. So two signals approach each other as shown here. At one instant, the signals completely overlap. Let's try to bring this signal to overlap with the other one. So I'm bringing this part here. Because they completely overlap, I think that part will come there. Then this part here will be here. And then this part here, I think it will cover up most of this part. And this will be there. So let's now try to sum up. According to the principle of superposition, this part will remain the same. And because this is in the horizontal, this part will not affect that one. So we expect our signal to have this part, that part. We notice that this part here will affect this one. In other words, it will take it slightly downwards. So the resultant there, according to the principle of superposition, will be slightly down. So this part here will go down slightly. But then this part here, a certain part here adds up with the other part of the other wave to give a larger displacement here. So this will be down here. So this part will not be affected. In other words, we're now going to have a resultant wave which is having that part. It goes slightly deeper. Then it comes slightly not very close to the original part here. So it will be like this. Then it goes up and it should take that shape. So this is exactly how in actual sense, this part here is what has been it has been affected, so it has been taken deeper. So we expect a signal which looks somehow like that. So let's check from the alternatives that we have to see which one matches. So we have exactly this one matches our answer, so the answer is going to be A. Okay. Coherent waves are produced at P and at Q and travel outwards in all directions. Coherent waves, remember coherent waves are those waves which maintain a constant phase difference between them. The line RS is halfway between P and Q and perpendicular to the line joining P and Q. The distance RS is much greater than the distance PQ. So the distance RS is much greater than the distance PQ. Along which of the lines shown is an interference pattern observed? Along which of the lines shown is an interference pattern? Along which of the lines is an interference pattern observed? So remember, at P and Q we have two coherent waves are produced. And these travel outwards in all directions. They travel outwards in all directions. So in other words, think of a sound wave. Sound wave, it travels in all directions. Then the line RS is halfway between P and Q. That means if a wave travels from P to S and from Q to S, that will give a constructive interference because they will travel the same distance. So if they arrive at S in phase, then they will give constructive interference. And since they maintain a constant phase difference, if we assume that they start from with a phase difference of 0, then at S we expect constructive interference. So along which of the lines shown is an interference pattern observed? So we have both R, S, and XY. We don't expect interference patterns along RS, so this one is wrong. RS only, we don't expect an interference pattern along RS. XY only, so we expect an interference pattern at XY, along XY, because waves from Q can also travel different distances, and they overlap around here. So we expect that there will be interference patterns above S, I mean to the right of S and to the left of S. Therefore, it is CX only. D is wrong because since these are two coherent sources, if they travel the same distance to point S and they form an interference pattern at S, then we expect interference patterns on both sides. Therefore, XY only is the answer to that question. A diffraction grating is used to measure the wavelength of monochromatic light, as shown in the diagram. The spacing of the slits in the grating is 1.0 times 10 power negative 6 meters. The angle between the first order, so this one is n equals to 1. Diffraction maximum is 70 degrees. So we divide this into 2 because the angle is always measured. The angle theta is always measured from the central bright fringe or from the central maximum. But here they say the angle between the first order diffraction maxima, that is plural, is 70. So that means the angle from the central to the first order maximum on one side is going to be 70 divided by 2, which is 35 degrees. So what is the wavelength of the light? So for a diffraction grating, we now know that n lambda is equal to d sine theta. So n is 1 because it's first order, and the wavelength is lambda. This should be equal to d. The spacing of the slits in the grating is 1 times 10 power negative 6. So this will be 1 times 10 power negative 6 sine of 35. So we check with our calculator. 1 exponent 6, 1 exponent negative 6 times the sine of 35. So this gives us 5.74 times 10 power negative 7. 5.74 times 10 power negative 7. The answers have been quoted as nano, but even if I don't change to nano, I see that the answer will be C. Because when you change this to nano, you divide this by 10 power negative 9, which gives us 574 nanometers. Which wave is a longitudinal wave? A light wave that is not longitudinal, a radio wave that is transverse, a ripple on the surface of water that is also transverse, a sound wave traveling in air that is longitudinal. A train that is moving in a straight line along a railway track has a whistle that continuously emits sound of frequency F. A woman standing by the side of the track hears sound of frequency 0.85 F. You notice that this frequency which is observed is less than the normal frequency of F, because 0.85 is less than 1. So the observed frequency is less. That means by all means, or this implies that by all means, because the woman is standing, it means the source must be moving away. So without even checking by calculation, I can first eliminate what is showing, or wherever is showing towards. So I will eliminate this one towards the woman, towards the woman. So what is the velocity of the train? What is the velocity of the train? So from observed frequency is equal to V over V, because it is moving towards, away from the woman, this will be plus the speed of the source, then times the frequency of the source. So the observed frequency is 0.85 F. The speed of sound is 340 divided by 340 plus the speed of the velocity of the train, which I'll call Vs, that is the speed of the source, then times the frequency of the source, which is F. So you'll notice that F has cancelled out. So just solve this equation. So this would be 340 plus Vs is equal to 340 divided by 0.85. So I'll just press my calculator. 340 divided by 0.85, that is 400. Then I take 340 to the right hand side, so I'll say minus 340, which gives us 60. So this is 60. Speed of the source is 60 meters per second, so which makes the answer to be C. Orange light in a vacuum has a wavelength 600 nanometers. What is the frequency of this? Since it is light, we know the speed. So frequency is going to be V over a wavelength, which is 3 times 10 power 8 divided by wavelength, which is 600 times 10 power negative 9. From our calculator, 3 exponent 8 divided by 600 exponent negative 9. So that is 5 times 10 power 14 hertz, which makes our answer to be D. A stationary sound wave has a series of nodes. The distance between the first and the 60th node is 30 centimeters. What is the wavelength of the sound? If it is hard for you to establish these nodes, you can just do this manually. So the first, this is 1, 2, 3, 4 nodes, 5, 6. So the distance between the first, let this be the first, and the 60th node is 30 centimeters. So this distance is 30 centimeters. What is the wavelength of the sound wave? Remember, the distance between two successive notes is half wavelength. So we have a wavelength, two wavelengths and a half. So 2.5 wavelengths equals to 30 centimeters. So it means 2.5 is 5 over 2, lambda is equal to 30, which means lambda is equal to 30 times 2 divided by 5. So that is 6 times 2, which is going to give us 12 centimeters. So this is 12 centimeters. So the answer is going to be D. Which diagram shows the diffraction of water waves in a ripple tank? Note very carefully, when diffraction occurs, the wavelength does not change. The wavelength does not change. So this is wrong automatically because there is no way diffraction patterns will bend towards the source. Yet this is the aperture is like the source of diffraction. Then secondly, this one is also not. This is showing some diffraction. The wavelength is remaining the same, but then the pattern of bending, we notice that the wavelength here is not very far away from the size of the gap, even though the size of the gap is smaller, but they are not. It is not very far away. Therefore, we expect that the diffraction patterns would start from close the gap, or they would bend closer to the gap. Therefore, it means B is also wrong. A is showing that there is completely no diffraction. It is actually just showing that part of the wave is just cut off and only remain with a small portion of the wave, which is just almost the same as the size of the gap. So this one is also wrong. So for diffraction, this is how diffraction occurs if the size of the gap is almost or closer to uh, the wavelength. So the answer is going to be C. A hill stands between a radio transmitter and a house. The radio transmitter cannot be seen from the house, but radio waves from the transmitter are received at the house. Why is this? Of course, this relates to wavelength. Radio waves have a longer wavelength, so they can easily undergo diffraction around the hill. So let's see the answers. The wavelength of light is longer than the wavelength of radio waves. The wavelength of light is longer than the wavelength of radio waves. Radio waves have the longest wavelength. The wavelength of light is shorter than the wavelength of radio waves, so there is more diffraction of light over the hill. There is more diffraction of light, no. more diffraction should be of radio waves. The wavelength of radio waves is longer than the wavelength of light, so there is more diffraction of radio waves. So this will be the correct answer. There is more diffraction of radio waves around the hill because radio waves have a longer wavelength. In an experiment to demonstrate double slit interference using light, the distance from the slit to the screen is doubled, and the slit separation is halved. The wavelength of the light is kept constant. By which factor does the separation of adjacent bright fringes change? So it is a double slit, and we know for a double slit, lambda is equal to AX divided by D. So let's check. Let this be the initial condition. The second condition, the wavelength lambda 2, they have said the wavelength is kept the same. So wavelength lambda 2 is the same as lambda. And the distance from the slits to the screen is doubled. So in the denominator, we have twice D. And the slit separation is halved. Remember, A is the slit separation, so we have a half A. By what factor does the separation of the adjacent bright fringes change? So we want to find x2. So you have that wavelength lambda is equal to a half, which is A times x2 divided by this a half takes the 2 down, so it is 2 times 2, which becomes 4D. 4D. So making x the subject, you will notice that or I can even substitute for lambda from the first part. So A times the first value of x, A times x, is going to divide by D is going to be A times x2 divided by 4D. So A cancels, D cancels, and this is giving us x2 being equal to 4 times x. So the answer is going to be 4. The second value of x will be 4 times the first value of x. So the answer is D. The graph shows how the displacement of a particle in a wave varies with time. Okay, which statement is correct? The wave has a period of 2 seconds. Let's check the period. So the period is 4, so this one is wrong. The wave has a period of 2 seconds. The period is 4. The wave has a period of 4 seconds, which is true, and it could be either transverse or longitudinal. It could either be transverse or longitudinal. The wave has a period of 4 seconds and must be transverse. This is not true. We can represent a transverse or longitudinal wave in the same way. We can represent, because for both, they have points where particles vibrate with maximum amplitude or maximum displacement, which we call amplitude. So this could be transverse or longitudinal, but is a progressive wave. Therefore, not a stationary wave, a progressive wave. Therefore, the answer is going to be C. The wave has a period of 4 seconds. It could be transverse or longitudinal. A wave travels along a coiled spring. The graph shows the variation with the time of the displacement of a point on the spring. So displacement against time. What is the frequency of the wave? So this is easy. Frequency is going to be 1 over period. And this is going to be 1 over. When we try to look for the period, you notice that I'll just take this part here. We have 1.5 cycles. 1.5 cycles take a time of 0.2. 1.5, a period is 0.2 seconds. So it means 1.5 is 3 over 2. 1.5 is 3 over 2 times the period is equal to 0.2 seconds, which means the period is going to be 2 times 0.2 divided by 3. So the period is 0.4 over 3. So this is going to be 1 over 0.4 divided by 3, which is going to be 3 divided by 0.4 in seconds. So we can check 3 divided by 0.4, and that gives us 7.5. So the frequency is 7.5. Note how I came up with the period. It was very hard for me to estimate here. You You can't say it is 0.15, but it was easy for me to see 0 and 0.2. So, and we counted 1.5 cycles, which are taking a time of 0.2. So I tried to find one cycle or one period by just getting 3t/2 being equal to 0.2. An electrical signal is displayed on a cathode ray oscilloscope. The time base is 50 milliseconds per division. The Y gain is 2 volts per division. What is the amplitude of the signal? So for amplitude, we look for the Y gain. And they have said 2 volts for every division. And here we have one division representing the amplitude. So straight out without calculation, since it is one division representing the amplitude and yet the Y sensitivity is 2 volts per division, the amplitude is simply 2 volts. A car traveling at a steady speed in a straight line passes close to a stationary observer. The observer measures the frequency of the sound from the engine. As the car approaches the observed frequency, so it approaches, that means the frequency is going to be high. The observed frequency is 220 Hz. When the car moves away, the observed frequency is 180 Hz. The speed of sound in air is 340. What is the speed of the car? So if it is moving towards, the denominator will be minus, and if it is moving away, the denominator will be plus. So we just substitute. Observed frequency 220 is equal to speed, which is 340, divided by 340. Because it's moving towards, this will be minus the speed of the car. Then times the normal frequency, I will call it Fs. Then if it is moving away, the observed frequency is 180. This will be equal to 340 divided by 340. Because it's moving away and the frequency is lower, this is going to be plus Vs times the frequency of the source Fs. So I'll just divide the two equations. So dividing the two equations, I have 220 divided by 180. Fs cancels out, so Fs has cancelled. And the 340 cancels out, so I just get the reciprocal of this. So the reciprocal will be 340 plus Vs over 340 minus Vs. Note that Fs cancels out when I divide the two equations. And the 340 in the numerator also cancels out when I divide the two equations. So I just get the reciprocal of the last the equation at the bottom. And then 340 plus Vs goes up, leaving 340 minus Vs in the denominator. So we just simplify this. I'll just simplify this. So this is going to be 11. This is by 2, this is 9. By 2, this is 11. So I have say 11 into 340 minus Vs is equal to 9 into 340 plus Vs. So I'm just going to collect like terms using my calculator. So I have 11 times 340, then minus 9 times 340. So that is 608 on one side. Then on the other side, I have 9 times Vs plus 11 Vs, which becomes 20 Vs. I just opened the brackets and collected like terms. So I now divide this by 20. So by 20 by 20. So I think that is 34. So Vs is 34. Therefore, our answer is going to be C. Which frequency of electromagnetic radiation could be ultraviolet? Ultraviolet, that is just after violet. Let's check the wavelengths because we are familiar with the wavelengths rather than the frequencies. So for the first one, I'll just press my calculator to get the wavelength corresponding. Wavelength, I'm using the formula wavelength is equal to V over lambda over F, where this is 3 times 10 power 8 divided by the value of F. So the first one is 3 exponent 8 divided by 1 exponent 6. So that is 300. That can't be ultraviolet. This is 300 meters. Then the second one, 3 exponent 8 divided by 1 exponent 9. That is not also, this is 0.3, which is still radio waves. The next one is 3 exponent 8 divided by 1 exponent 12. That is 3 times 10 power negative 4 meters. It is still on the left hand side of the visible spectrum. So it means our answer is going to be D, because Rumenera's mother is visiting Uncle Xavier's garden. So visible light, on the left hand side of visible light, we have 7 times 10 power negative 7. And remember, radio waves have the highest wavelength. So wavelength increases in this direction here. So, and ultraviolet is on the other side. So these values here are on the left hand side of visible light. That's why the answer is going to be D. An electromagnetic wave travels in a straight line through a vacuum. The wave has frequency 6.0 terahertz. What is the number of wavelengths in a distance of 1 meter along the wave? Number of wavelengths. So let's first find the wavelength corresponding to 6 terahertz. So wavelength is equal to V, which is 3 times 10 power 8, divided by frequency, which is 6 times 10 power tera is power 12. So we have 3 exponent 8 divided by 6 exponent 12. So that is 5 times 10 power negative 5 times 10 power negative 5 meters. So that is, what's the number of wavelengths in a distance of 1 meter? So one wavelength is 5 times 10 power negative 5. So a distance of 1 meter, we shall say 1 divided by the answer, which is 20,000, which is 2 times 10 power 4. And that means our answer is going to be C. A beam of laser light is directed towards a narrow slit. After emerging from the other side of the slit, the light then falls on a screen. What is the pattern of light seen on the screen? So because it is passing through a narrow slit, when it passes through a narrow slit, we expect it to undergo diffraction, and the diffraction is going to be symmetrical around in the horizontal plane. It is not going to be, if diffraction occurs, it's going to be symmetrical in a horizontal plane rather than in the vertical plane. So that means we ignore A and we ignore C. Then D is showing that diffraction is occurring in all directions around the slit, which is not going to be possible. Therefore, the answer is going to be B. B is showing that on both sides, on the left and on the right of the slit, the wave spread in the regions of the geometrical shadow. Therefore, the answer is going to be B rather than any of the others. So C would be wrong, because C would just show that the image of the slit is what is being formed on the screen. There was no diffraction. Yet B shows that there is diffraction, and we know that diffraction occurs when light passes through a very narrow slit. Okay, the diagram shows 4 pairs of waves. In each case, the displacement y measured at a fixed point is plotted against time t. Which pair of waves is not coherent? So remember, for coherent waves, they maintain a constant phase difference throughout. They maintain a constant phase difference throughout. So let's check. So check the initial phase difference here. The particle here is vibrating upwards and is at equilibrium. The particle here is downwards and is at maximum displacement. And you notice that it is the same, it is being maintained every time. It is being maintained every time. And we still check the second one. These are in antiphase. We can check it is antiphase all through. In B, 180 degrees out of phase. Then in C, we notice that the particles here are vibrating downwards. These are vibrating upwards. Then we are going to look for the same point again. When we look at it again, here it is vibrating upwards, it is vibrating downwards, which is still maintained. We look at a similar point again, it is vibrating upwards, it is vibrating downwards. We look at this point again. Okay, so it appears as if that part, the phase has been maintained. Well, let's check another part. So you notice that if you check this part and the next part and check them again, it's like the phase difference between these two waves is not being maintained at all. It's like the phase is changing after some time. They are not maintaining a constant phase difference. That's what we mean by the waves not being coherent. So the answer is going to be C. For D, you notice that the phase here is maintained, the phase here is still maintained, and so on and so forth. So it is only going to be C, that the phase difference between the wave above is not the same as the phase difference, or is not the same as that the phase of this is not the same as this, so they are said not to be coherent because they don't maintain a constant phase difference, or they don't have a constant phase difference throughout. If you try to look for corresponding points every time, you notice that there will be a change. There will be a change in the phase. Therefore, they are not coherent. With which types of wave can the Doppler shift be observed? Doppler shift can be observed by all types of waves. Although in sound we commonly call it Doppler shift, in light we normally call it redshift. So this is going to be with all waves. A distant star is receding from the Earth with a speed of 1.74 times 10 power 7. It emits light of frequency 4.57 times 10 power 14 Hz. The speed of light is 3 times 10 power 8. The Doppler effect formula can be used with light waves. What will be the frequency of the light when detected on Earth? So observed frequency is going to be V divided by V minus, because the distant star is receding, if recede is to move away, so this is going to be plus. The observed frequency is going to be lower. So plus the speed of the source times Fs. What will be the frequency of this light when detected on the Earth? So the observed frequency is going to be the speed of light, which is going to be 3 times 10 power 8 divided by 3 times 10 power 8 plus the speed of the source, which is the star. It is moving at 1.4 times 10 power 7. Then we multiply this by the normal frequency, which is 4.57 times 10 power 14. So we have 3 exponent 8 divided by 3 exponent 8 plus 1.4 exponent 7, then times 4.57 exponent 14. So the answer is 4.37 times 10 power 14. 4.37 times 10 power 14 Hertz. So the answer is going to be B. The graph shows the variation with the time of the displacement of two separate waves X and Y. Wave X has a frequency F and amplitude A. What is the frequency and what is the amplitude of wave Y? So you notice that wave Y has a bigger amplitude, and if wave X has amplitude A, which is represented by 1, 2, 3, 4, 5 small squares. Then amplitude B has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which is twice. So it means the amplitude of Y is going to be twice. So we eliminate A and C. Then we can check the frequency. You notice that the frequency of wave X is f, and there is a full cycle in half a cycle of wave Y. So it means the frequency of wave Y is a half of the frequency of wave X. If frequency of wave X is f, then frequency of wave Y is less than f. It is actually half, because um, a full complete cycle of wave X fits in half a cycle of wave Y. So the frequency of wave Y is going to be a half of f, which therefore makes our answer to be B. Diffraction is a term used to describe one aspect of wave behavior. What does diffraction make possible? The ability to hear sound, to hear around corners. Okay, that is diffraction. The ability to hear high frequency and low frequency, that is Doppler effect. It's not diffraction. The ability to hear loud and quiet sounds, that's not diffraction. The ability to hear sound through a brick wall, that's not diffraction. So diffraction is the ability to hear around corners, because sound waves can undergo diffraction around a corner. The diagram represents the pattern of stationary waves formed by the superposition of sound waves from a loudspeaker and their reflection from a metal sheet, not shown. W, X, Y, and Z are 4 points on the line joining the center of these waves. Which statement about these stationary waves is correct? An antinode is formed at the surface of the metal sheet. That's not true. On the metal sheet, we expect a node to be formed there. A node is a quarter of wavelength from an adjacent antinode. A node, if this is the antinode, note that a node to a node, that is half wavelength. That means a node to the antinode is again half of half wavelength, which is a quarter of wavelength from an adjacent. Adjacent means to the next antinode. So the answer is going to be B. A node is a quarter of wavelength from an adjacent antinode. In other words, the distance between two successive node and antinode is always a quarter of wavelength. Then the distance between a node and the next node is half wavelength. The distance between an antinode and the next antinode is also half wavelength. Monochromatic light of wavelength 5.3 exponent -7 meters is incident normal on a diffraction grating. The first order maximum, that means n is 1, is observed at an angle of 15.4 degrees to the direction of the incident light. What is the angle between the first and second order diffraction maximum? So we need to find the angle for the second order, because the first order angle has been given. Using the first order, we can find the spacing between the slits. For diffraction grating, we know that n times lambda is equal to d sine theta, which means our value of d is going to be sine n, which is 1, times wavelength, which is 5.3 times 10 power -7, divided by sine theta, which is going to be sine of 15.4. That is our value of d. Using that value of d, because it's the same diffraction grating, we shall now change small n to 2. So substituting in this formula again, n is 2 times wavelength, which is remaining the same, 5.3 times 10 power -7 is equal to d, which d is 5.3 times 10 power -7 divided by sine of theta, which is sine of 15.4, then sine of theta. I've just substituted in that equation, so this one has cancelled. So I have that sine theta is equal to 2 sine of 15.4. So I'm getting theta 2 sine 15.4, and again I get this the sine inverse of the answer, which is 32. So it means this theta 2 is going to be 32 degrees. Theta 2 will be 32 degrees, but we want what's the angle between the first and the second order diffraction. So if this is the diffraction grating, and somewhere here we have the screen, so the central order maximum is this one, the first order is this one, the second order, and we want this angle here. This angle here is the difference in the angle between the second order and the first order. So if this is theta 1 and that is theta 2, so the difference is going to be 32 minus 15.4. Minus 15.4, which gives us 16 point, that is 16 point, I think that is 16.7. 16.7 approximately. 16.7. If I can say 32 minus 15.4, that is 16.6, or approximately 16.7, because I rounded. Writing 32, I rounded off to a whole number, so the answer is going to be C. Two sound waves have frequency 250 Hz and 300 Hz. The speed of sound is 340 meters per second. What is the difference between the wavelengths of the two waves? So there are two sound waves, and sound has 340. So we can just find the wavelength of each. For the first one, remember wavelength is going to be V over frequency F. For the first one, it is going to be 340 divided by F, which is 250. For the second one, it is going to be 340 divided by F, which is 300. Then we find the difference. So 340 divided by 250, that is 1.36. The second one is 340 divided by 300. That's 1.13 recurring. So we find a difference. 1.36 minus the answer, which is 0.0, means 0.23. So the difference is approximately 0.23. So the answer is going to be A. Which electromagnetic waves have the wavelength of 10 power negative 2? Of course, we now know that 10 power negative 2 is going to be microwaves. 10 power negative 2 is microwaves. So we can first eliminate that one. So we eliminate A and D, because we know 10 power negative 2 must be microwaves. Then I think 10 power negative 10 must be X-rays. So we just look for X-rays. 10 power negative 10 is X-rays. So it means our answer is going to be B. You can use a different elimination method. 10 power negative 13 is gamma rays. So it means this one would be correct. 10 power negative 13 is gamma rays. So it means we still have these two. Then 10 power negative 5 is automatically infrared, because visible light stops on 10 power negative 7. So this is infrared. 10 power negative 5, microwaves 10 power negative 2, 10 power negative 2. Gamma rays 10 power negative 13, X-rays 10 power negative 10, or 10 power negative 11. Which statement concerning a stationary wave is correct? You know that for a stationary wave, all particles vibrate in phase in the same segment, but they have different amplitudes, and particles vibrate out of phase with particles in the neighboring segment. In fact, they are in antiphase. So A, all the particles between two successive nodes oscillate in phase. That is very correct. If this is one segment and the other one is another segment for a stationary wave, we expect a node there, a node there, a node there. Particles in this part here between two successive nodes are always in phase, but they are out of phase. In fact, they are 180 degrees out of phase with the particles in the next segment. In other words, particles between two adjacent antinodes are 180 degrees out of phase in a stationary wave. Continuous water waves are diffracted through a gap in a barrier in a ripple tank. Which change will cause the diffraction of the waves to increase? Note that for the diffraction of the waves to increase, the size of the gap must be almost of the same order as the wavelength itself. Okay. Increasing the frequency, of course, increasing the frequency decreases the wavelength. Reducing the width of the gap, reducing the width of the gap. Sorry, increasing the width of the gap, reducing the wavelength of the waves, reducing the width of the gap. So continuous water waves are diffracted through a gap in a barrier in a ripple tank. In a ripple tank. You must have seen this in school, in a ripple tank. So increasing the frequency, of course, that reduces the wavelength. Increasing the width of the gap, that will make diffraction even less pronounced because most of the waves will just pass through. Reducing the wavelength of the waves, this makes them even smaller. It is similar to the first one. These two are the same. Reducing the width of the gap. Reducing the width of the gap, this makes the width of the gap to be almost of the same order as the wavelength of the water waves, which makes diffraction to be maximum. A parallel beam of light of waves 415 nanometers is incident normal on a diffraction grating, which has 300 lines per millimeter. 300 lines per millimeter is the same as 300 times 1000 to make it lines per meter. What is the total number of intensity maxima? So we want N maximum. Remember, for a diffraction grating, N lambda is equal to D sine theta. So for N maximum, sine theta is equal to 1. Therefore, N is going to be D, which D we don't know, but we know that D is the same as 1 over the number of lines. So this is going to be 1 over 300,000. Sine theta is equal to 1. Remember, sine theta equals to 1. We have this in mind. So 1 over 300,000, we take lambda in the denominator, so that will be times 450 times 10 power negative 9. So we have to open our brackets. We'll just start with 300,000 times 450 exponent negative 9. Then 1 divided by the answer. That is 7.407. We round off to the smallest whole number, which is 7. So N is equal to 7. I'm saying N is 7. We cannot round off to the next number. We always round off to the smallest number. Now we want the total number of intensity maximum. So N equal to 7 means 7 above the central maximum and 7 below the central maximum, then plus the central maximum. So the total number is going to be 7 times 2 plus 1. 7 above, 7 below, then plus the 0 order maximum, which gives us 15. Fringes of separation X are observed on a screen 1 meter from a double slit that is illuminated by yellow light of wavelength 600 nanometers. At which distance from the slits would fringes of the same separation X be observed when using blue light of wavelength 400 nanometers? For a double slit, Young's double slit, we know that lambda is equal to A times X divided by D. So at what distance from the slit? So we are going to change D. So I will not change the units for wavelength. I'll just get two equations. For the first condition, wavelength is 600 equals to A. A is the slit separation, it is not changing, and same separation x, so x is remaining, and D was 1 meter. For the first case, D was 1 meter. Then the second one, we have 400, and slit separation is the same, fringe separation is going to remain the same, and D is not known. So we combine these two equations. So I'll just bring AX here so that I have 400 is equal to, where there is AX, I'll put there 600 divided by D, because 1 meter does not change anything. So it means D is 600 over 400, which is 6 divided by 4. That's 1.5. So our answer is going to be D. The diagram shows a cathode ray oscilloscope being used to measure the rate of rotation of a flywheel. The flywheel has a small magnet M mounted on it. Each time the magnet passes the coil, a voltage pulse is generated, which is passed to the CRO. The display of the CRO is 10 centimeters wide. The flywheel is rotating at 300 revolutions per minute. So this one is going to help us to find the period. This is the frequency. Number of revolutions per unit time is going to be the frequency. Let's use it to find the period. So frequency is going to be 3000 divided by 1 minute, which is going to be 60 seconds. So now this is the frequency in hertz. Then it implies that the period is going to be the reciprocal, which will be 60 divided by 3000. So 60 divided by 3000, that is 0.02. So this is 0.02 meters, seconds. 0.02 seconds. So that is the period. So which time-based setting will display clearly separate? Clear, this is the most important part. Separate pulses on the screen. First of all, they should fit on the screen and they should be clearly separated. So we are just going to check every time-based setting here to see the separation between the slits that it gives. If the separation is reasonable and they can fit on the screen, then it means we can take it. So let's say the period between the period between the pulses is equal to the length or the distance between the pulses times the time-based setting. So we are going to always check for L. So T is going to remain fixed, 0.02. Then divide by the time-based setting. So we're always going to check with the time-based setting. Let's start with the first one. The first one is 1 second per centimeter. Remember, this is in seconds, so let's check. 0.02 divided by 1 second per centimeter. Divide by 1, so that means it will be 0.02 centimeters. So for the first one, it will give us 0.02 centimeters, which is very small. It means they cannot be displayed on the screen. This one gives us L. Distance between the pulses are 0.02 centimeters. This cannot be they cannot be displayed on the screen because the distance between them is extremely small. We can't see them clearly. We check the second one. Using the same formula, the period is 0.02 seconds. Divide by 10 exponent -3. So this gives us 2 centimeters. So this one gives us L as 2 centimeters. 2 centimeters can easily be seen on the screen, and it means we can have two pulses which can clearly be, we can have pulses which are separated by 2 centimeters. Let's check the third one also. Period of pulses between pulses 0.02 divided by 100 microseconds exponent -6. 200 centimeters. That one cannot fit on the screen because our screen is only 10 centimeters. This one gives us distance between the pulses as 200 centimeters. They can't fit on the screen. Let's check the last one. 0.02 divided by 1 exponent -6, because it is micro, 20,000. So this one gives us L as 20,000. This one can also not fit on the screen, so our answer is going to be B. A microphone connected to the Y plates of a cathode ray oscilloscope is placed in front of a loudspeaker. The trace on the screen of the CRO is shown in that figure. The time-based setting is 0.5 milliseconds per centimeter. The Y plate sensitivity is 0.2 millivolts per centimeter. What is the frequency of the sound from the loudspeaker, and what is the amplitude? Let's start with the amplitude because it is easy. So I'll just count peak to peak. 1, 2, 3, 4, 5, 6. So it means I divide into 2, 6 divided by 2, that is 3. So the amplitude is represented by 3 centimeters. So the amplitude is going to be 3 centimeters times the Y sensitivity, 0.2 millivolts per centimeter. And per centimeter cancels, so the amplitude must be 0.6. So D is wrong and B is wrong. Then let's check the frequency. To find the frequency, we need 1 over the period, which is 1 over the length representing 1 cycle. So 1 cycle, I want you to notice that we can easily identify 1 cycle by starting from this point up to this point. That is 1 cycle. Or you can identify half a cycle from this point to this point. Then the other half is the other one remaining. So it means 1, 2, 3, 4, 5, 6. 6 small squares represent 1 cycle. Those are 6 centimeters. So 6 centimeters, period is 6 centimeters, 1 over 6 centimeters times the time-based setting, which is 0.5 multiplied by 10 power negative 3 to change it to seconds. So it is seconds per centimeter. Per centimeter cancels out with the centimeters. So this is going to be 6 times 0.5 exponent -3. Then we get 1 divided by the answer, which is 333.3 recurring, that is 330. Therefore, our answer is going to be A. The source of sound of frequency 1000 Hz moves away from a stationary observer at a speed of 30 meters per second. The speed of sound is 330. What is the frequency of the sound heard by the observer? It is moving away, so observed frequency is going to be V over V plus Vs times Fs. Vs is standing for the speed of the source, and Fs is standing for the frequency of the source. So the observed frequency is going to be V, which is 330, divided by 330, plus the speed of the source, which is 30, then times 1000. So we have 330 times 1000 divided by 360. So that is 919.6 recurring. 919.6 recurring, which is 917. So our answer is going to be B. Each of the principal radiations of electromagnetic spectrum have a range of wavelengths. Which wavelength is correctly linked to its radiation? Some of these frequencies should now be part of you by now. X-rays cannot be 10 power negative 14. This will be gamma. And gamma cannot be 10 power negative 9. So you have eliminated those two. You can now check from the two remaining from the radiations. Remunera's mother is visiting Uncle Xavier's garden. You use the visible spectrum for reference. This is 7 times 10 power negative 7 for red, and 4 times 10 power negative 7 for violet. So it means violet should have a power which is smaller than -7. So that is -8, -9, or even -7. Then infrared is next to, it should have a power less than or greater than -7, such as -6, -5, and so on. Microwaves is very fun. We know the wavelength of microwaves is approximately 10 power -2. So it means the answer is going to be C. 10 power -5 is approximately infrared. A stationary wave is set up on a stretched string. The diagram shows the string at two instants of time when it has maximum displacement. The oscillations of point P on the string have amplitude A. What is the distance moved by P from the position shown in the diagram after half a time period of the wave? Let's look at the diagram. So the oscillations of point P on the string have amplitude A. What is the distance moved by P from the position shown in the diagram after half a time period of the wave? After half a time period of the wave. So it is at maximum displacement downwards. So after it will move to the equilibrium. If I put in equilibrium here, so it will move to equilibrium. It has moved the distance A, that is a quarter cycle. Then it moves to the maximum amplitude, the other side, that is another half of a quarter of a cycle, which is half a cycle, which is half a period. So it will move from this point to the other point. That means it will have covered twice the period. So the answer is going to be A. I mean C, twice the period, twice the amplitude. It is at maximum displacement at the bottom. A quarter period will go to equilibrium, and another quarter period goes to maximum displacement on the other side. Therefore, it will have covered the distance which is twice A. Which statement is an example of the diffraction of light? Diffraction of light. Number one, addition of the amplitudes of two beams of light. That's not diffraction, that is superposition. The change in the direction of a beam of light, that could be a reflection or even refraction. The separation of a beam of white light into a spectrum of colors using a prism. Actually, that would be similar to diffraction, but that is actually dispersion. It is not really diffraction, because diffraction should result into interference maximum. The separation of a beam of light as it passes through a small hole. So that will be diffraction. It must be passing through a narrow slit or around an edge, not passing through a prism. So the answer is D. Spreading, actually. Not separation, spreading. Sound waves of wavelength lambda are emitted by a loudspeaker and pass through two slits P and Q. Two sound waves from the slits meet at R. Okay, two sound waves meet at R. What is the condition for an intensity maximum loud sound to be detected by a microphone? So an intensity maximum loud sound, that is constructive interference. For constructive interference, two waves must arrive at a point in phase. So two waves must arrive at a point in phase. The amplitudes of the two waves at R must be the same. Even if they're not the same, for a maxima, it can be formed even if the amplitudes are not the same. For a minimum, even if the amplitudes are not the same, it is formed. But for zero intensity, the amplitudes must be the same. Distance PQ must be smaller than a wavelength. That one is not necessary. The two waves from the slits must have traveled the same distance to R, even if it is not the same distance, as long as they arrive in phase. So the answer is going to be D. Coherent light passes through a double slit, producing bright and darker fringes on a screen placed parallel to the plane of a double slit. The intensity of the light from each of the slits is initially the same. The intensity of the light passing through one of the slits in the double slit is now increased. Oh, this is very beautiful. Intensity is now increased. If the intensity is increased in a double slit, we expect that where we saw bright fringes, they are actually going to be brighter. Where we saw bright fringes, we expect them to be actually brighter. And where we saw darker fringes, because the intensity has been increased, where we expect if we saw dark fringes, they will not be necessarily darker, but the intensity of the dark fringes is also going to be high. So they will not be too much dark, they will not be darker as before, they will be actually brighter, I can put like that. So what is the effect on the appearance of fringes on the screen? Separation of fringes is not affected by intensity, so it means A and B are cancelled out. Then maximum intensity of darker fringes. When the intensity in one of the slits is increased, the bright fringes become more brighter and the darker fringes are still brighter. They will not be as dark as they were before. If the intensity in one of the slits is decreased, the bright fringes become less brighter, but the darker fringes will be brighter. Because for darker fringes, total cancellation can no longer occur if the intensity is not the same. Remember, total cancellation occurs when the amplitude is the same. Intensity is directly proportional to amplitude squared. If intensity is not the same, the amplitude is not the same. So total cancellation is not expected as long as the intensity in one of the slits is not the same as that in the other slit. Therefore, the answer here is going to be C. There will be no change in separation, but the darker fringes, the intensity, maximum intensity of darker fringes becomes greater. The following trace is seen on the screen of a CRO. The setting of the time base is then changed from 10 milliseconds per centimeter to 20 milliseconds per centimeter. And the Y plate sensitivity remains the same. If the Y plate sensitivity remains the same, it means the amplitude is going to remain the same. So begin by that. What trace is shown? So begin by eliminating amplitude. This one shows the amplitude as double. That is wrong. Here the amplitude has remained the same two boxes. Here the amplitude has remained the same two boxes. Here it has been doubled, so these two are wrong. We remain with the two where we are going to check the frequency or the period. So the period here was represented by 4 boxes. Note that period is equal to the length representing one cycle times the time-based setting. When the period was represented by 4 boxes, I will do this locally. When the period was represented by 1, 2, 3, 4 boxes, the length, okay, let me just use one cycle. So the period was T when the length of this was 4 boxes, and the time-based setting was 10. 4 boxes, that is 4 centimeters. Let me change this to 4 centimeters because each box is 1 centimeter. So this is 4 centimeters times the time-based setting, which is 10 times, okay, 10 milliseconds per centimeter. So it means the period is represented by 4 centimeter or 4 times 10 milliseconds. That is the period. Now we are going to change this. The new period T should be equal to the length, which we don't know, times the time-based setting, which is 20 milliseconds. because the setting of the time base is then changed from 10 milliseconds to 20 milliseconds. So it means if the time base setting is changed from 20 milliseconds to from 10 milliseconds per centimeter to 20 milliseconds per centimeter, 20 milliseconds per centimeter. If the time base setting is changed, it means the period has been increased. The period must have been decreased because the frequency is actually going to be increased. The frequency must have been increased. Okay. So initially period was 4 times 10 milliseconds, and this was represented by 1, 2, 3, 4 boxes. Now the time base setting has been increased. It means the period doubles. If the period doubles, it means the frequency must be halved. Therefore, the number of cycles which fit in where we had 4 boxes for one cycle, if the time base setting has been doubled, then it means the frequency must have been halved. Therefore, this will mean we shall have in 4 boxes, we shall have 2 complete cycles. So our answer is going to be C. Our answer is going to be C. Okay. A beam of red laser light has length 1 meter. What is the order of magnitude of the number of wavelengths of red light in 1 meter? So that one is, it's a beam of red laser light. It has length 1 meter. What is the order of magnitude of the number of wavelengths of the red light in 1 meter? Number of wavelengths of red light in 1 meter. So we know that red is normally approximately, the wavelength of red is approximately 7 times 10 power negative 7 in meters. One wavelength of red is approximately 7 times 10 power negative 7 in meters. How many wavelengths are those in 1 meter? So 1 divided by 7 exponent negative 7. So this is 1.4 times 10 power. I'm interested in the power of 10. So that is 1, 2, 3, 4, 5, 6. So that is 10 power 6. So this is going to be B. The answer there will be B, because when I get 1 divided by 7 times 10 power negative 7, this gives us 10 power 6 approximately. So the answer is going to be B. When a car traveling with a constant velocity passes a stationary observer, the observer hears a change in the frequency of the sound emitted by the car. Which statement is correct? When a car traveling with a constant velocity passes a stationary observer, the observer hears a change in the frequency. So we know that when it is approaching, the frequency is higher, and when it is receding, the frequency is lower. The change in the frequency is greater as the car moves away. That's not true. The greater the speed of the car, the greater the change in the observed frequency. The greater the speed of the car, the greater the change in the observed frequency. Let's check. Observed frequency is equal to V over V minus or plus Vs, then times Fs. So they're saying the greater the change, the greater the speed of the car, that is the speed of the source, the greater the change in the observed frequency. Of course, the speed of the source determines so much the change in the observed frequency, so that would be making sense. The observed frequency is lower as the car moves towards. That's not true. The volume of the sound heard by the observer does not change as the car approaches. Volume of sound doesn't make any sense, so the answer is going to be B. The intensity I of the sound is inversely proportional to the square of the distance x from the source of the sound. This is represented by that equation. So let's write an equation here. Intensity I is going to be equal to a constant k divided by x squared. Air molecules at point P, a distance r from the source S, oscillate with the amplitude 80 micrometers. Point Q is situated a distance twice r from S. What is the amplitude of oscillation of air molecules at Q? Okay. Let's begin by coming up with the two equations using this one here for intensity. Intensity with the distance x from the source. So intensity at P is equal to K divided by the distance from the source to P, which is R squared. That is intensity at P. And intensity at Q is going to be equal to the same constant divided by the distance from S to Q, which is twice R, but this is squared. Okay, we have used intensity. Now let's look at the amplitude. We know that intensity is directly proportional to amplitude squared. So let's come up with two equations again. Intensity at P is, in terms of amplitude, is going to be, they gave us the amplitude at P is going to be a constant K times the amplitude, which is 8 squared. Then intensity at Q is going to be a constant times the amplitude at Q, which is squared. So we now have these equations. We are just going to combine them using intensities inversely proportional to R. I have that IP divided by IQ is equal to K cancels. So I have 2R squared divided by R squared. I've divided the two equations. I get the reciprocal of the last one in the denominator. And also, I have that IP over IQ is equal to K8 squared over KA squared. So this is going to be also equal to K8 squared over KAQ squared, because we want the amplitude at Q, so K cancels out. So I just equate these two. Squaring that one gives us 4R squared over R squared equals to 8 squared over amplitude of Q squared. So R squared cancels. So we notice that amplitude of Q squared is going to be 8 squared divided by 4. 8 squared divided by 4, I think that is 8 squared divided by 4. Is it 16? No, this is squared. So this is 16, but this is squared. Then I find the square root. So AQ squared is 16. Then I find the square root, which is going to be 4. So AQ is equal to the root of 16, which is going to be 4. So our answer is going to be D. A diffraction grating with n lines per meter is used to deflect light of various wavelengths lambda. The graph shows a relation between the deflection angle theta and wavelength for different wavelengths in the nth order interference pattern. What is the gradient of the graph? So for a diffraction grating, it is a diffraction grating. We know that n times lambda is equal to d sine theta. So making sine theta the subject, sine theta is equal to n over d. It is n over d times lambda. So they have plotted a graph of sine theta against lambda. So notice that the gradient is equal to n divided by d. But remember, d is 1 over n, 1 over capital N, which is the number of lines. So it means the gradient is n divided by 1 over capital N, which becomes small n times capital N, which makes our answer to be A. Which wave phenomenon is not needed to explain the pattern of observable fringes produced by double slit experiment. Which wave phenomenon is not needed to explain the pattern of observable fringes? Observable fringes. So coherence is needed, diffraction is needed, they should spread. Interference, they should overlap. Reflection is not needed, so the answer is D. They should be coherent, coherence is needed, they should maintain a constant phase difference. Diffraction is needed, they should spread into regions of geometric shadow. Interference is needed, they should overlap or they should superpose. So those three are needed for observable interference, for observable fringes. A student uses a cathode ray oscilloscope to measure the period of a signal. She sets the time base of the CRO to 5 milliseconds per centimeter and observes the trace below. The trace has length 10 centimeters. What is the period of the signal? So we can see this. So this is 1, 2, 3.5. 3.5 cycles have a length of 10 centimeters, meaning 3.5 is the same as 7/2. This is 1, that is 2, that is 3 cycles and a half. So that is 7/2 cycles is 10 centimeters. That means one cycle is going to be represented by 2 times 10/7 in centimeters. So we can now find a period. Period is equal to the length of one cycle, which is 2 times 10/7 in centimeters, times the time base setting, which is 5, times 10 power negative 3 seconds per centimeter. So per centimeter is cancelled out. So 2 times 10 times 5 exponent negative 3 divided by 7. So this gives us 0.014. 0.014, which is 1.4 times 10 power negative 2, which makes the answer to be D. The table shows the wavelengths of 5 electromagnetic waves, which row correctly identifies the principal radiation for each of these radiations. By now, you should be knowing which wave has the longest wavelength, that is radio waves, and which wave has the shortest wavelength, which is gamma rays. You should be knowing the principal radiations for microwaves as 10 power negative 2 or negative 3. So we can start with what we know. Microwaves should have negative 2. Microwaves should have negative 2. So where it is not negative 2, it is wrong. So this is wrong automatically. And B is going to be wrong. And C is also going to be wrong because it is giving microwaves negative 10. Then we know radio waves have a higher wavelength than X, and should have a higher wavelength than all the other radiations. So here it is showing radio waves have the smallest 10 power negative 10, which makes, of course, these two are still wrong. So we have to choose between A and D. We know that radio waves have the longest wavelength, which they are the only radiations with a positive power of 10. So we have to choose, these two are still correct here. Microwaves are still correct here. Now we have to choose from this point here. We can choose either from this point, gamma rays and X-rays, or we can choose from X-rays and infrared. We can choose from X-rays and infrared. So on the visible spectrum, we have Rumenera's mother is visiting Uncle Xavier's garden. So from the visible spectrum, on the left-hand side, we have 7 times 10 power negative 7 for red. So infrared is going to have a power of 10, which is greater than negative 7. That could be negative 6. So here it has been given negative 10. So it means this row is going to be wrong. So D is wrong. D is automatically wrong. And if D is wrong, it means we remain with one option, which is X-rays. So gamma rays, X-rays, infrared, microwave, then radio waves. That would be the order. The graph shows the variation with the time of the displacement x of a gas molecule as a continuous sound wave passes through a gas. The velocity of sound in the gas is 330 meters per second. All the graphs below have the same zero time as the graph above. What is the displacement time graph for a molecule that is a distance 0.165 meters further away from the source of the sound? 0.5165 meters further away from the source of the sound. So let's first find the wavelength of this wave. So the period is going to be 500 microseconds. The wavelength, remember V is equal to lambda times F. They gave us, so it means wavelength is going to be 330 divided by F. This one is going to be the same as lambda over T. So it means lambda is V times T. So this is times T, which is 500 times 10 power negative 6. So 330 times 500 exponent negative 6. So they are giving us a wavelength 0.165 meters. That's the wavelength. So the question is, what is the displacement time graph for a molecule that is a distance of 0.165 meters further away from the source of the sound? So it means 0.165 meters is one wavelength. So it means the molecule would be repeating a similar pattern just like the one that we saw at t equals to 0. So if at t equals to 0, this is what we are seeing. Then after a distance of 0.165 meters further away from the source, a new wavelength will be starting. Therefore, we should have a similar pattern like this one, because a new wavelength would be starting. Therefore, this one is not going to be correct. This one is not going to be correct. This one is not going to be correct. A new wavelength similar to the one that we had would be starting. Therefore, the answer is going to be D. After one wavelength, the pattern looks exactly the same as the initial pattern. After a second wavelength, it again looks the same. Of course, at half wavelength, it would be like this. Half wavelength, it would be like that. Just the mirror image. A quarter wavelength, it would look like this. So this is half wavelength, a quarter wavelength, and so on and so forth. The warning signal on an ambulance has a frequency 600 Hz. The speed of sound is 330 meters per second. The ambulance is traveling with a constant velocity of 25 meters per second towards an observer. Initial position of the ambulance, then we have the observer. This is towards, this is away. Which overall change in observed frequency takes place between the times at which the ambulance is a long way behind and when it is a long way in front of the observer? I think we answered such a question, but we can still answer it. The frequency here towards, so speed is 330, normal frequency is 600, divide by 330. Because it is towards, we subtract the speed of the source, so minus 25. Then here, if it is away, normal speed is 330, normal frequency is 600, divided by 330. Because it is away, we add, so this will be plus 25. So we can press the calculator to get these two values and subtract. 330 times 600 divided by 330 minus 25. So this is 649.2. 649.2. Let's check the other one again. 330 times 600 divided by 355. So that is 557.7. 557.7. So we want the change, overall change, so we subtract. So 649.2 minus 557.7, which gives us 91.5, or approximately 91. So because of rounding off, that's why it is giving us 91.5, but is approximately going to be 91 if we don't round off. Diagrams X and Y show the passage of water waves around an obstacle and through a gap. The thick lines are barriers to the waves, and each thin line represents a wavefront. Okay. Which statement is correct? Diagrams X and Y both illustrate diffraction. Okay. Not diagrams X and Y. Of course, here we are seeing it starts undergoing spreading through regions of geometric shadow. So they are both representing diffraction. Diagrams X and Y both illustrate interference. Not at all. Only diagram X illustrates interference. Not at all. Only diagram Y illustrates diffraction. So the answer is A. Diffraction can be spreading around an edge, or it can be spreading as the wave goes through a narrow path or a narrow gap. The diagram shows a long rope fixed at one end. The other end is moved up and down, setting up a stationary wave. What is the phase difference between the oscillations at X and Y? That is automatically zero because they are in the same segment. Particles between two adjacent nodes vibrate in phase, so the phase difference there is zero, without wasting any time. A diffraction grating is used to measure the wavelength of monochromatic light. The spacing of the slits is 1.15 times 10 power negative 6 meters. The angle between the first order, so n equals to 1, is 60 degrees as shown. What is the wavelength of the light? So for a diffraction grating, n lambda is equal to d sine theta. So we want to find the wavelength. The wavelength is going to be d, that is the slit, spacing of the slits, 1.15 times 10 power negative 6 sine. Where there is theta, theta will divide this into 2 because theta is measured from the central bright fringe, central maximum. So this will be sine of 30. Divide by n is equal to 1 because it was first order. So this is 1.15 exponent negative 6 times sine of 30. So we are seeing that the wavelength is 5.75 times 10 power negative 7. 5.75 times 10 power negative 7 meters, which is automatically 575 nanometers. So the answer is going to be C. A cathode ray oscilloscope displays a waveform as shown in the figure. So these are pulses. The time interval between two adjacent peaks of the waveform is 0.006 seconds. What is the time-based setting of the CRO? The time interval between two adjacent peaks. So two adjacent peaks are represented by, this is a half, this is another half. So this is 1, 2, 3. So 3 centimeters, or 3, is it in centimeters? 3 divisions. So 3 divisions are representing the time interval between two adjacent peaks of the waveform is 0.006 seconds. So this is going to be L, or the time interval, which is 0.006 seconds, is equal to L, which is 3 divisions, times the time-based setting, which I'm calling X. So X is going to be 0.006 seconds divided by 3 divisions, which is going to be This is going to be 0.0002 seconds per division. Per division is -1 power -1. So that is going to make this the answer, I guess, because when I move 1, 2, 3, that is 2 milliseconds per division. So the answer is C. High frequency sound waves with the frequency 2 megahertz travel with a speed of 2 kilometers per second through a liquid. What is the shortest distance between a compression and a rarefaction? Remember, distance between two successive compressions is going to be wavelength. Distance between two successive rarefactions is wavelength. Therefore, distance between one compression and the next rarefaction is half wavelength. So we first find the wavelength. So wavelength is equal to the speed. They gave us the frequency and the speed. So wavelength is the speed divided by frequency. 2 kilometers, that is 2000 meters per second, divided by 2 times 10 power 6, because it is mega. So we have 2000 divided by 2 exponent 6, which gives us 1 times 10 power -3, then divide by 2, because we have to get half wavelength, which is 5 times 10 power, that is 5 times 10 power -4 in meters. So distance between a compression and a rarefaction is half wavelength, which we have seen as 5 times 10 power -4 meters. We can check, we can change it into millimeters, so that divide by meters to millimeters, we multiply by 1000, so that is times 1000 to bring milli times 1000, which is a half, 0.5. So our answer is 0.5 in millimeters. A transverse progressive wave of wavelength lambda is set up on a stretched string. The graph shows the variation of displacement y with distance x at a particular instant. The displacement where distance x is equal to lambda over 8 is y1. What are the next two values of x where the displacement y is again equal to y1? That is very easy. I can draw a horizontal line through y1. So it means this point here, the displacement will still be y1, but what is this value here? It means I have to subtract lambda minus 8 from lambda minus 2. So that value is going to be lambda over 2 minus lambda over 8. LCM is 8. 8, that is 4 lambda minus lambda, which gives me 3 lambda over 8. So the next one should be 3 lambda over 8. C and D are going to be wrong. Then the next one should be here. That means on wavelength, I'm going to add lambda over 8. So the wavelength plus lambda over 8. LCM is 8. 8, that is 8 lambda plus lambda, which is 9 lambda. So our answer is going to be B. A man standing next to a stationary train hears sound of frequency 400 Hz emitted from the train's horn. The train then moves directly away from the man and sounds its horn when it has a speed of 50 meters per second. The speed of sound is 340 meters per second. What is the difference in frequency of the sound heard by the man on the two occasions? So let's just find the frequency when it is at 50 meters per second. Since it will be away, observe the frequency is equal to V over V plus Vs times Fs. So that one is going to be F naught equals to V, which is 340, divided by 340 plus Vs, which is 50, then times Fs, which is 400. So we shall have 340 times 400 divided by 340 plus 50, that is 390. So that is 348.7. Now we want the difference, so we just subtract minus 400, or 400 minus that answer. So the negative does not matter. I just wanted 400 minus that answer. Difference in frequency is 400 minus 348.7, which gives us 51. So the answer is going to be A. Observable interference fringes are produced using light from a double slit. The intensity of the light emerging from each slit is initially the same. The intensity of the light emerging from one of the slits is now reduced. One of the slits. How does this affect the interference pattern? We have already seen if the intensity in one of the slits is reduced, it means the brighter fringes become less brighter. But because for the darker fringes there is no more destructive interference, the darker fringes will become brighter or less darker. They will no longer be as dark as they were before because total cancellation has stopped or has reduced. So bright fringes and dark fringes all become brighter. Bright fringes and darker fringes all become brighter. The bright fringes and the darker fringes all become darker. That one is not possible. The bright fringes, because it has been reduced, total cancellation is no longer there. The bright fringes become brighter and the darker fringes become darker. Total cancellation is not there. The bright fringes become darker because the intensity reduces. That is very true. The bright fringes become darker or less brighter. The darker fringes become brighter, so the answer is going to be D. But I have said if it was increased, the bright fringes would become brighter. But again, the darker fringes also become brighter. We can't say the darker fringes become darker. There's nothing like becoming darker. Darker fringes are only dark when there is total cancellation. That's when the intensity is the same. If the intensity is not the same, we don't expect extremely dark fringes. So total cancellation is not expected as long as the intensity is not the same, because it means the amplitudes will not be the same. Monochromatic light of wavelength 450 nanometers passes through two parallel slits 0.3 millimeters apart. Bright fringes are observed on a screen 2 meters away. How far apart are the bright fringes? So that is x. For a double slit, lambda is equal to ax divided by d. So x is going to be lambda, which is 450 times 10 power negative 9. D is 2 meters divided by a. Slit separation is 0.3 times 10 power negative 3. So 450 exponent negative 9 times 2 divided by 0.3 exponent negative 3. So that is 3 times 10 power negative 3, which times 1,000 becomes 3.0 millimeters. So it means the answer here is going to be C. A microwave transmitter is placed at a fixed distance from a flat reflecting surface as shown in the figure here. A microwave detector is moved steadily in a straight line from X to Y. A series of maxima and minima of intensity is obtained. The distance between adjacent maxima is 1.5 centimeters. So distance between adjacent maxima, two adjacent maxima, those are points of maximum interference or constructive interference. Let me use C for constructive interference. Is always half wavelength. It's like having a distance between two adjacent antinodes is half wavelength. Two adjacent nodes is half wavelength. Two adjacent points that are two adjacent resonance points is half wavelength. So it means this distance will give us wavelength as 2 times 1.5 centimeters, which is going to be 3 centimeters. And it is a microwave. It means we know the speed, which is the speed of light. So our frequency is going to be the speed divided by the wavelength, which will be 3 times 10 power 8 divided by the wavelength, which is 3 times 10 power negative 2. So 3 exponent 8 divided by 3 exponent negative 2. So that is 1.0 times 10 power 10, which makes the answer to be C. A whale produces sound waves of frequency 5 Hz. The waves are detected by a microphone and displayed on an oscilloscope. What is the time-based setting? So we just look for one cycle. One cycle is 2 divisions. So frequency, we know that frequency is equal to 1 over period, which is 1 over the length representing one cycle times the time-based setting. So the frequency, which is 5, is going to be 1 over the length representing one cycle is 2 divisions, then times x, which is time-based setting. So it means x is going to be 1 over, remember this is per second, hertz is per second. So x is going to be equal to, I'm making x the subject, to be 2 times 5 per second, then times division. So when this goes up, 1 over 10, 1 divided by 10 is 0.1. So this is 0.1. Then per second goes up, it becomes seconds. And then per division goes up, division goes up, it becomes per division. So the answers here we have 0.1 millisecond per division, 1 millisecond per division, and we have 10 milliseconds per division. When we change this to milliseconds, we divide by 10 power negative 3. So answer divided by 1 exponent negative 3. To bring in milli, it becomes 100. So this is 100 milliseconds per division. So the answer is going to be D. A sound wave moves with a speed of 320 meters per second through air. The variation with the time of the displacement of an air particle due to this wave is shown in the graph. Which statement about the sound wave is correct? The frequency of the wave is 500 Hz. Let's check the frequency. Frequency will be 1 over period, which period is 4 milliseconds. So that's 4 times 10 power negative 3. 1 divided by 4 exponent negative 3. It is 250. So the frequency is 250 Hz. So it means A is not going to be correct. The graph shows the sound is a transverse wave. That is not true. A transverse or longitudinal wave can both be represented by that displacement time graph. The intensity of the wave will be double if the amplitude is increased to 0.4. Remember, intensity is directly proportional to amplitude squared. So that is not going to be true. The intensity cannot be twice doubled if the amplitude is increased to 0.4. That is if the amplitude is doubled. The wavelength of the sound wave is 1.28. Let's check the wavelength. It is sound, the speed is 320. So wavelength is going to be V over F, or V over T. V times T, or V times T. V is 320 and the period is 4. The period is 4 times 10 power negative 3. So we can check 320 times 4 exponent negative 3, which is 1.28. So the answer is going to be D. The wavelength of the sound is 1.28 meters. A wave of frequency 15 Hz travels 24 meters per second through a medium. What is the phase difference between 2 points 2 meters apart? Phase difference between 2 points that are 2 meters apart. Let's first find the wavelength. Wavelength is going to be V over F, which is 24 divided by 15. That's the wavelength. 24 divided by 15, which is 1.6. So to find the phase difference, this will be 360 into the distance apart over the wavelength. So this will be 360 into the distance apart, which is 2 meters, divided by wavelength, which is 1.6. So this is 2 divided by 1.6. That is 1.25. So I'll just take the 0.25. But anyway, 1.25 times 360, that is 540. So if 540 is not there, then I will say 360, subtract 360 from 540, because 360 means phase difference is 0, but then the other balance is going to be, so this is going to be 450, which is 360 degrees plus a quarter a cycle, or plus 90. So this part here is showing that the phase difference is going to be a quarter. They're going to be out of phase by a quarter a cycle because of 90 degrees. So this is 360 plus 90 degrees. So it means there is no phase difference. That's not true. They are out of phase by a quarter of a cycle. That is true, because 90 degrees is a quarter a cycle. So this part here is what causes the phase difference. So it is either 450 degrees or 90 degrees, or you go on adding 90 to 360, 90 plus 360, 90 plus 360, and so on and so forth. A wave of amplitude A has intensity 3 watts per meter squared. We know that intensity is directly proportional to amplitude squared. So for the first one, 3 equals to a constant times a squared. What is the intensity of a wave, same frequency, that has amplitude twice a? So intensity I2 is going to be a constant into twice a, but this is squared. So we combine the two equations. So from the first equation, it means k is equal to 3 over a squared. I'll substitute for k. So the second equation, I2 is going to be k, which is 3 over 2 over a squared times 4 a squared, and a has cancelled. So this gives us 12 watts per meter squared, which means our answer is going to be D. The electromagnetic wave has a wavelength that is numerically of the same order of magnitude as the diameter of a nucleus. In which region of the electromagnetic spectrum does the wave occur? Same order, has wavelength that is numerically of the same order as the magnitude of the order of a nucleus. Of course, it is approximately 10 power, same order of magnitude as the diameter of a nucleus. The diameter of a nucleus is approximately 10 power negative 14. For an atom, it is 10 power negative 10 meters. This is atom, and this is a nucleus. In which region of the electromagnetic spectrum does the wave occur? That is automatically gamma rays. This one is X-rays, 10 power negative 10 meters, but 10 power negative 4. The diameter of an atom, nucleus, is 10 power negative 4, which is actually the wavelength of the gamma ray. Remember, for X-rays, I've said it is 10 power negative 10. Visible light is 10 power negative 7. Infrared is normal 10 power negative 6. Micro is 10 power negative 2. Radio is 10 power 2, and so on and so forth. The diagram shows a stationary wave on a string at 2 instants of maximum vertical displacement. Frequency is 12 Hz. What is the speed of the wave? So first find the wavelength. So we have, this is one wavelength and a half, which is 3 over 2 lambda is equal to 90 centimeters. So it means wavelength is 2 times 90 divided by 3. So that is 30 times 2, which is 60 centimeters. So speed V is equal to lambda times F, which is lambda is 60 times 10 power negative 2 times F, which is 12. 60 exponent negative 2 times 12, which is 7.2. So V is 7.2 meters per second. A loudspeaker emitting sound of frequency F is placed at the open end of a pipe of length L, which is closed at the other end. A standing wave is set up in the pipe. A series of pipes are then set up with either one or two loudspeakers of frequency F. The pairs of loudspeakers vibrate in phase with each other. Which pipe contains a standing wave? Which pipe contains a standing wave, or which pipe contains a stationary wave? Okay. So we notice that if this was a closed pipe and the fundamental mode is formed here, a series of pipes are then set up with either one or two loudspeakers of frequency F. The pairs of loudspeakers vibrate in phase with each other. Which pipe contains a standing wave? So here we expect that for a closed pipe, the fundamental mode of vibration F is going to be equal to V divided by, remember, the length of the pipe L is going to be representing, the length of pipe L will represent, this is going to be a quarter of wavelength. So this will be equal to, lambda is going to be 4L, so this is going to be 4L. That is for the fundamental mode. So it means if the pipe is, if this one is twice L, because a standing wave is set up in the pipe, a series of pipes are then set up with either one or two loudspeakers of frequency F, the same frequency F. So this one has length 2L and the frequency of the sound is F. That means this one here, this one will not produce a stationary wave, because if the frequency needed here for this same length, because this is an open pipe on both sides, here F, the frequency here, the frequency needed to cause here a stationary wave is equal to V, because this is a half L, a half lambda. The frequency needed here is twice L, V over 2L, which in comparison with this one, the frequency needed to cause a stationary wave is going to be twice F naught if the pipe is open and on both sides and the same length. The same applies to this one here. And so these two will not form a stationary wave. Then let's check this closed one. If the length is 2L, and note that the frequency is F. To cause a stationary wave here, the frequency required, F is going to be equal to V divided by, because 2L is equal to a quarter of a wavelength, so it means Vf is going to be equal to 2L times 4, which is going to be 8L. It means the frequency needed to cause a stationary wave, the frequency needed to cause a stationary wave would be 16 times F naught. It should be 16 times F naught. That means our frequency F cannot cause a stationary wave here, because the fundamental mode here is V over 8L. Let's check this one. This one is an open pipe on both sides. For the fundamental mode of vibration, we have something like that. That means twice L is going to be equal to, this is half wavelength, which is going to be half lambda, which means that lambda is going to still be 4L. That means the fundamental frequency here is going to be V over lambda, which is 4L, and it is the same as the frequency, the fundamental frequency here. So since this is the frequency provided, it means this one will form a stationary wave. Therefore, our answer is going to be D. In a double slit experiment, the distance between the fringes on a screen was too small to measure. What would increase the distance between the fringes? Double slit. For double slit, lambda is equal to ax over d. We want to increase x. Either we increase wavelength, either we increase d, or we decrease a. Increase the distance between the light source and the slits. That one does not affect because d is not the distance between the light source and the slits. D is the distance between the slits and the screen. Increase the distance between the slits and the screen. That one will automatically increase x because we see that D is directly proportional to x. So the answer is going to be B. Two light waves of the same frequency are represented by the diagram. What could be the phase difference between the two waves? So we look for the time out of step. Corresponding values of time out of step. This is going to be very hard, but okay, this is at this point here, approximately, and the corresponding peak is here. So it means that this is phase angle. So that is, this is displacement against phase angle. What could be the phase difference between the two waves? Okay, so here we have this is 100. This is 100. Okay, so if I consider this is at 100 degrees, the particle here is vibrating downwards, but this has reached equilibrium. The particle there, this is passing equilibrium. The particle here has reached the particle here is vibrating downwards and is at its maximum displacement. Okay, so what could be the phase difference between the two waves? Let's check. So this is going to be, let me check, 150. To 60 minus 180, that is 80 to 6, no, this is once, okay, that is 360 minus 150, no, that is not true, 360 minus 220, that's 140, this phase difference is 100, so we have 360 minus 100, that is 260. So this is going to be the phase difference between the two waves could be 260. That is after considering one cycle. You can also check 360 minus 330. That is 30 by the phase angle between these 2 points is 100 degrees. So that would be 360 minus 180, which gives us, no, 360 minus 100, which gives us 260 degrees. That could be the phase difference between the two waves. The sound wave has a speed 330, frequency 50 Hz. What's the possible distance between 2 points on the wave that have a phase difference of 60 degrees? So phase is equal to 360 into distance apart over wavelength. The wavelength is going to be V over F. So wavelength is going to be V, which is 330 divided by 50. So wavelength is going to be 33 over 5. So phase is 60 degrees equals 360 degrees into what is the possible distance between the 2 points. So that distance is x, and wavelength is 33 over 5. So that is 5 over 33. So I will have 60 divided by 360, then times 33 divided by 5. So that is 1.1. So our answer is going to be B. So x is 1.1. What is not an essential condition for an observable interference pattern to occur between the waves from two sources? Not essential. The frequency of the two sources must be equal. That is very essential for an interference pattern. Frequency and wavelength must be the same. The sources must be coherent. That is very essential. They must maintain a constant phase difference. The sources must emit waves of equal amplitude. For an observable interference pattern, what is not essential for an observable interference pattern to occur? So the sources must emit waves of equal amplitude. This may not be necessary. That is only necessary for zero intensity. So that may not be very essential. The waves from the two sources must overlap. This is very essential for interference. So this is not very essential. So let's stop there for part 5. See you in part 6. These videos are still continuing because waves is too long. I hope you learned something from this. We shall start from this same question next time. Bye bye.